Hello and welcome to this important, you can call it a revision class, which in which we shall discuss with numerical problems the entire ionic equilibrium chapter. We shall leave aside the molecular equilibrium, which makes use of gaseous reactions involving at least one gas. And the equilibrium is molecular. No ions, no solution is involved. But here we shall be doing with molecules and ions, mostly in aqueous solution. And this class is going to be very, very important for those who are IIT and NEET aspirants. If you have already done this chapter with great intensity, with great depth, it's well and good. If you have not done or you have forgotten with time, so you are studying so many chapters, so many subjects, so you can revise with me. Hello and welcome those who are watching from the YouTube directly, live streaming. Welcome. We are going to have a discussion on the entire, is a very big chapter, ionic equilibrium. We shall be discussing the whole chapter in 2 hours with numericals. Let me share my screen first. Yes, Suraj Singh, how can I help you? He writes, please help me. How can I help you? Let me know. If it is ionic equilibrium, yes, I'm going to help you now. Just I'm going to help you now. And if it is other than ionic equilibrium, so I can't help you now. Maybe later I can help you. Let's start. Now, I told you that this chapter deals with ions as well as molecules in aqueous solution. We shall not be discussing anything with non-aqueous solvents like liquid ammonia, like chloroform, carbon tetrachloride. So those solvents will not be discussed. Whatever we'll be doing, that is an aqueous solution. And there are 2 types of ionic equilibria. In fact, let us call it equilibria. The plural of equilibrium is equilibria. So one is homogeneous, just like we did in molecular equilibrium, simply called chemical equilibrium. We had homogeneous and heterogeneous. Here also in aqueous solution, we have homogeneous and B heterogeneous. In homogeneous, we shall be talking of acids, bases, salts, salts of different types, and then a mixture of salt and acid or base. that is called the buffer solution. So all these four aspects, acids, pure bases, pure salts, and there are three types of salts. In fact, five types. Salt of weak acid, strong base, salt of strong acid, weak base, salt of strong acid, strong base, salt of weak acid, weak base, and the fifth one is amphoteric salt or amphiprotic salt. So we'll discuss about all these salts. And then mixture of acid or base plus salt. That will be called a buffer solution, which maintains the pH at more or less a constant value. The change of pH is minimal, particularly in a pH range which is close to the pKa or pKb, as we shall be talking about that. These are called buffers. These are very important solutions which are mostly required for all biological enzymatic bioprocesses. All bioprocesses are held are or bioprocesses happen at constant, more or less constant pH. If there is a significant change in the pH, then human being or any living being will immediately die. Metabolic activities will stop. So to maintain the pH, not to allow a sudden spike in the pH, we or the nature makes use of buffers, which consists of a salt and acid or a base. So just like blood has a carbonic acid and bicarbonate buffer, bicarbonate buffer, which maintains at a slightly alkaline region. So many biological, biochemical processes happen at a constant pH condition. We'll talk about that. And heterogeneous is only solubility product principle, where a sparingly soluble salt like silver chloride, like silver chromate, like barium sulfate, there are many sparingly soluble salts which we normally call insoluble. Now in +2 level we call them sparingly soluble salts. For them, this is heterogeneous ionic equilibrium, a solubility product principle. And in salts also we'll discuss how salts undergo hydrolysis. And there also will be of salts. And also we shall be talking of theory of indicators, how indicators help in indicating you through the color change, through the drastic color change, the onset of equivalence point. The equivalence point, when one equivalent of a base reacts with one equivalent of an acid, that is called the equivalence point. That is indicated by the color change. Theory of indicators. So we shall be first, in all these cases, the important aspect is the pH. How to measure hydrogen ion concentration. That Sorensen used the word pH, potenge, hydrogen ion, potenge, power. That is, as I told you know it, minus log to the base 10. Actually, it is activity. It is activity of hydrogen ion. Activity is the effective concentration, is not effective molarity or concentration. Actually, it is a product of the molarity into an activity coefficient, say F. This is called activity coefficient, which is in many cases in a concentrated solution in presence of added ions, it is not 1, it is less than 1. So here we are using molarity, this one. Sometimes we write as H plus. That is the molarity. But out of supposing it is 0.2 m, actually 0.2 moles per liter, 0.2 moles of hydrogen ion per liter of solution will not be available. A part of it will be defunct. So the available H plus ion for real conductivity, which gives the pH. So for dilute solution that we are doing for you, F is equal to 1. This is called activity coefficient. Activity coefficient is 1 for dilute solutions. So the molarity is same as activity. So we can call it hydrogen ion concentration. This is pH. And in pure water, there is auto ionization, H2O plus H2O. One H2O will produce proton, the other H2O will accept proton. So one which will accept will be H3O plus and OH minus. This is called autoprotolysis, and we simplify. Instead of writing 2 water, we write 1 water, and we reduce the bulk, make it H plus. Actually, as you know, naked H plus ion doesn't exist inside water. It has to be in the form of H3O plus at least. But while solving problems, we write this is the dissociation of water. And in pure water, as you know, this Ka or which is equal to Kb of water, because it is producing H plus and also OH minus, is equal to H plus concentration into OH minus concentration by water concentration. And this is called Kw, the product of the two ions, Kw, ionic product of water. And this is water concentration. And if it is 10 to the power minus 14 at 25 degrees Celsius, and the molarity of water is 55.55, molarity of pure water, because 1 mole is 18 gram, and 1000 milliliter solution is nothing but 1 liter. There is no solute. In that way, you have to find out no solute, the same solute, solvent, only one entity. So 1000 milliliter is equal to 1000 gram. As you know, the density of water is 1 gram per milliliter. By 18, it comes to 55.55. So if you divide, it will be what about something 1.8 and something like that, 10 to the minus 16, something like that. And if you take just check it. And if you are joining with me, Ruchi Bist 3766, welcome. Be with me, you'll find the I'll be evolving the topic, presuming that you have at least been exposed to this chapter in whatever way you have been, it is known to you, but at least you have heard the terms. This is a revision class, and what I say, ionic equilibrium at a glance. If you can chat with me in the chat box, if I do some wrong calculation, please rectify me. If I write check, then you can do at home or now itself with your calculator. And so H plus ion in pure water is equal to OH minus ion at 25 degrees Celsius is root over of this is 10 to the minus 7. This is pure water or in perfectly neutral solution. But if it is acidic, as you know, H plus ion will be greater than OH minus ion. That means it will be greater than 10 to the minus 7. Which one? H plus. And OH minus will be less than 10 to the minus 7. But always this product will be constant. This has to be constant. If this increases, this decreases. If this decreases, this increases. But the product will be always 10 to the minus 14. And let me remind you, you get questions when temperature is raised, the bond breaks more easily. So more H plus, more OH minus, although in the same quantity in pure water. So Kw increases, it becomes 10 to the minus 14 at 40, say at 50 degrees Celsius, it might be 10 to the minus 13. So each one will be, say 10 to the power 6.5, 10 to the power 6.5, it increases. And say at 100 degree, it is 10 to the minus 12. So 10 to the minus 6, 10 to the minus 6. So both Kw and H plus OH minus both increase with increase in temperature as the bond is broken with more and more ease. Similarly, in basic solution, if it is basic, the other way around, OH minus ion is greater than H plus. And you know, when you talk of pH is equal to 7, which is also equal to pOH for pure water or perfectly neutral solution. And pH plus pOH will be equal to 14. This is minus log H plus and this is minus log OH minus is 14. So if pH is known, you can find pOH. Usually, if pOH is determined first, but you are asked to find pH, you subtract pOH from 14. That is the way. So in acidic solution, as you know, pH is less than 7. Consequently, pOH will be greater than 7. The sum will be always 14. And in basic solution, pH is greater than 7. Consequently, pOH will be less than 7. The sum will be always 14. And for pure water or perfectly neutral, pH is same as pOH is equal to exactly 7. Now, with this much of introduction about pH, we have not yet studied the most important theory, the Bronsted-Lowry theory of acids and bases. Now, as you know, acids are proton donors which can donate proton, and there are two types, all protonic acids like HCl, HBr, HI, H2SO4 and all. These are 7 strong acids. HI number 1, which is same as perchloric acid. Then number 2 is HBr, number 3 is HCl. And then number 4 is H2SO4, then 5 is HNO3, then HClO3. And of course, there are sulfonic acids belong to this category. Organic sulfonic acids are strong acids. These are strong acids. Strong acids at moderate concentrations are believed to be 100% dissociated. Even 0.1 m or 0.2 m concentration, the acid is believed to be 100% dissociated. So, virtually although their pKa values, I'll tell you, pKa values are different. This is -10, this is -10, this is -7, and it goes on, increasing. Less the pKa value, greater is the acid strength. I'll tell you about that just now. But in water, in moderate concentration, they all behave as the Ka value becomes -1.74. That is the Ka of hydronium ion H3O plus. I'll tell you. आगे आगे देखिए होता है क्या. But if concentration is very high, 10 molar, 18 molar, then the degree of dissociation, even if it is strong acid, is not 1. It's not 100% dissociated. In that case, K values will differ, and we have to find out what is the H plus ion concentration, just like we do for weak acids and bases using the Ostwald dilution law. To do that, similar manner. But moderate concentration, dilute solution, all are converted to H3O plus. That means virtually it is H3O plus. So only the variation of concentration makes the pH different. But Ka value, interestingly, for all these acids, although their pKa values are different, but the pKa value of dilute solution is same. So we say all strong acids, they level up their Ka values to the Ka value, pKa value of hydronium ion, that is -1.74. So we don't think much of strong acids whose pKa values are negative. It goes to 0, then positive values, then the Ka value becomes 10 to the power negative something, become weak acids and weak bases. So these are proton donors, are weak acids like acetic acid, like formic acid, like phenol, like carbonic acid, like phosphoric acid. This is a triprotic acid, diprotic acid, S2S, HCN, monoprotic. S3PO3 is a diprotic. One hydrogen is directly bonded. S3PO2 hypophosphorus, monoprotic. So these are weak acids. Can be diprotic, triprotic, but these are weak acids. The Ka values are less than less than less than 1, 10 to the power minus something. Oh, sorry. She was my granddaughter from US. So she didn't know that I am having a class, fixed class. Now these are all weak acids. These are strong acids. But whatever may be the acid, supposing it is a monoprotic acid. It may be strong, it may be weak. Let us talk about any monoprotic acid. Actually, H2 should be there, H3 be H3O plus, and its equilibrium constant will be called acid dissociation constant. The equilibrium constant for this process is called acid dissociation constant. So let us make it look simple. Remove water, because that K equilibrium multiplied by 55.55 is Ka actually. Remember this, Ka includes 55.55. So is nothing but H plus we write for H3O plus, A minus, I'm sorry, by HA. The H2O concentration 55.5 has been included in equilibrium constant to make it Ka. So this is less than 1 for weak, 0 or minus, less than 1. Not 0, less than 1. 10 to the minus 5, minus 6, not 0, I'm not talking of 0. Less than 1. And if it is greater than 1, 10 to the power maybe 0 is 1, or 10 to the power 3, 10 to the 4, 10 to the 5, then greater than 1, then that is a strong acid. And every value is made simple mathematically by making P. pKa is minus log A, all to the base 10. So for strong acids, pKa is negative. When we say negative, is less than 0. So supposing 10 to the power 10 is the Ka of Hi, which is a strong acid. Strong acids are much, the power factor will be 3, 4, 5, 6, minimum 3, 4, 5, 6, 7, 8, 9, 10, like that. So they are almost completely dissociated even at moderate concentration. So, and therefore pKa will be minus log 10 to the power 10 is equal to minus 10. If you see a negative sign in the pKa value, that is a strong acid. They will level up. Ultimately, in dilute solution, their K values are not minus 10, minus 7, minus 3. They are minus 1.74, because all are dissociated into hydronium ion, and hydronium ion has a, I'll tell you how, Ka value, pKa value of minus 1.74. Okay. Similarly, for strong acids, Ka of say acetic acid is 1.8 into 10 to the power minus 5. Is less than 1. But pKa will be greater than 0, is positive. Minus log 1.8 minus minus 5, that is plus 5. Log 10 is 1, so plus 5. So it will come 4.74 approximately. So that is plus. So when you find pK for weak acid, this is strong acid is negative, and for pK for weak acid is positive. More the positive values, weaker is the acid. So more the pKa value, positive pKa values, weaker is the acid. That means 10 to the minus, supposing 10 to the minus 10 is the Ka value of hydrogen cyanide, HCN, or hydrocyanic acid. So pKa is equal to 10. 10 to the minus 10 becomes plus 10. Similarly, more the negative values, stronger is the acid strength. Similarly, we talk of Bl bases. There are two types of, these are proton acceptors. It's not that. Arrhenius theory we won't discuss here. The uh, substance which produces H plus ion in water is acid, and which produces OH minus in aqueous solution is base. That is the outdated Arrhenius theory. But all the pH concept is based on Arrhenius theory, no doubt. But we will be discussing all our concepts based on BL theory, Bronsted-Lowry theory. So proton acceptors, the one which can accept a proton, there are two types, all negative ions. And out of positive ion, out of neutral, all neutrals, when I say neutrals, having lone pair. At least one lone pair is required. With the help of that lone A1, B2, they are conjugates of each other, and water and H3O plus, they are also conjugates. Water is the conjugate base of H3O plus. H3O plus is the conjugate acid of H2. So any two species which differ by one H plus ion are called conjugates of each other. So you might be wondering why I'm writing, how long I will write, and this vast chapter, how long I can finish. Well, these are the concepts, the fundamental aspect. If you are not clear, then to catch up, the other things will be mechanical and difficult. But if you understand this, what I am going to tell in another 25 or 30 minutes, it will be easier on your part to understand every concept, particularly the homogeneous equilibrium, ionic equilibrium. Then I shall give you the concepts of heterogeneous, the solubility product principle. So any two species differing by a single H plus ion are conjugates of each other, right? And interestingly, the Ka1 into K Ka into Kb is equal to 10 to the minus 14. When I say Ka into Kb, I mean the Ka of certain acid and its conjugate base. You know what is the conjugate base? Is Kb of the conjugate base. Their products will be same as 10 to the minus 14. You will be wondering how. Don't worry, but you remember this. That means what I am going to say, that if HCN has a Ka is equal to say approximately 10 to the power negative 10, then its conjugate base, can you tell me what is the conjugate base of HCN? Write down in chat box. Anyone watching? Anyone watching in the YouTube video, can you write down what is the conjugate base of HCN? HCN is the acid. The base is yes, it is Cn minus. So the Kb of Cn minus is 10 to the power minus 14 by 10 to the power minus 10 is equal to 10 to the power minus 4. What does it mean? Kb of Cn minus, I told you in the definition all negative ions are Bl bases. So under that definition, Cn minus comes under base, Bl base, and HCN is a protonic acid, comes under acid and a weak acid because Ka is so less than 1. Now, how you prove that Cn minus is a base? It is for ordinary, average students, we have to explain through hydrolysis of salt. But for you, cyanide ion is a base. So base means, acid means it has to have water. Unless there is water, the equilibrium won't happen. The ionic equilibrium will not happen. So this will accept a proton, becomes HCN, and it will leave behind free OH minus. However small it may be, OH minus, it is free. But HCN is a weak acid. The H plus ion produced from HCN is far, far less than the free OH minus ion which is produced by so-called hydrolysis. But I used to say the basic dissociation of Cn minus or hydrolysis. You can also say hydrolysis of salt containing Cn minus. So this constant, I will call it Kb, but many people call it Kh, is equal to right hand side, the product of right hand side concentration, that is produced, HCN produced from it due to hydrolysis or basic dissociation, and OH minus, which are same, the concentration of OH minus and HCN is same, and Cn minus. Water is included in this Kb, Kh, everything. So this is the Kb, and the HCN, which itself has its own dissociation, which is very, very small, as you know, 10 to minus 10 is this. And its Ka will be the right hand side product of the right hand side species and HCN. So if you multiply Kb with Ka, so-called Kh, I say Kb or Kh into Ka, you will find everything will cancel out. So you find SCN, SCN, Cn minus, Cn minus. So it is reduced to H plus into OH minus, which is nothing but Kw. That is why the fundamental principle is Ka and Kb of conjugates will be equal to Kw. And similarly, pKa plus pKb of conjugates is equal to 14, is equal to pKw, that is equal to 14. Of course, at 25 degrees Celsius, goes without saying. So if I ask you, supposing I take acetic acid, pKa is 4.74 because Ka is equal to 1.8 into 10 to the minus 5. So pK minus log of this is this. And I'll ask you what is the pKb of acetate ion. When acetate ion means it's salt. You can't buy 5 kg or 1 kg or 500 gram of acetate ion. If you ask some chemical house, give me 1 kg of acetate ion, he will laugh at you. So are you a fool? Are ions available freely? So it must be in the form of a salt. So sodium acetate. So it contains acetate ion. Sodium ion is absolutely a non-entity. It will not have any, because it forms an ionic compound. It doesn't hold anything in covalent bond. So it doesn't undergo any ionic dissociation. Doesn't produce any H plus or OH minus ion. Right? So that means acetate ion, the pKb will be 14 minus 4.74, 9.9. 0.26. So if this is this, you can find out Kb is equal to 10 to the minus 14 by 1.8 into 10 to the minus 5. So if you take 110, this will be how much? 5 point, same thing, 5 like that into 10 to the power minus 15. Oh, sorry, minus 14. I'm sorry, minus 14, minus 15. And here I forgot to write down, it is 10 to the power minus 5. So it is 5.55 into 10 to the power, it is minus 5, this is minus 10. See, therefore the pKb is 9.26. Okay, then compare with SCN, which we have already done. pK is equal to 10 because 10 to the minus 10, pK is 10. So pKb of cyanide ion is equal to 4. So this is 10 to the power minus 10. This is 10 to the minus 4. So what we found, if an acid is weaker, HCN is a weaker acid than acetic acid because its pK is 10 and its pKa is 4.74. So more positive is the pKa, weaker and weaker and weaker is the acid strength. And therefore, the opposite will happen for the conjugate base strength. Conjugate, I am not, Cn minus as a base is stronger than acetate ion. See how? Because the pKb is 4 here and acetate ion pKb is 9.26. So lower the positive P value, pKa or pKb value, stronger is the strength. If it is base, stronger is the base strength. If it is acid, stronger is the acid strength. So if certain acid is stronger than the second acid, then the conjugate base of the first acid will be stronger than the conjugate base of the second acid. So the strength of conjugates are inversely related on a comparative basis. That means if a certain base is stronger than the other base, then the conjugate acid of the first base will be weaker than the conjugate acid of the second base. So the strengths of conjugates are inversely related in a comparative basis. If a certain acid is stronger, its conjugate base is weaker. This is all in comparative. This is in a comparative basis. Not that certain acid is stronger, its conjugate base is really certain acid is weaker, like HCN. Its conjugate base is really a strong base. Sorry, its conjugate base is a really strong base. No, it's 4. 4 is still 10 to the minus 4. Anything negative, 10 to the power negative, or in pK it is positive, it is weak. Still it is weak base. But comparatively, Cn minus is a stronger base than acetate ion. But both are weaker bases. But much stronger. How many times? Nearly, say 9, 10 to the 5 times stronger. 10 to the 5 times stronger is cyanide ion. But it cannot compete with OH minus ion. I'll tell you what is OH minus ion. What is its pK and pKb? I'll tell you. It cannot compete with amide ion, NH2 minus. So it cannot compete with the carbonyl. It cannot compete with the alkynide ion. It cannot compete with hydride ion. So these are really strong bases. Their pKb values are really, really negative. Okay, then now let us talk about the autoprotolysis. I mean, this one we were talking about. If pKa of is 15 point, how much? 7. Then what is the pKb for OH minus ion? Because these are conjugates. As acid, its conjugate base is OH minus. So pKb of OH minus is equal to 14 minus 15.74 is equal to minus 1.74. So OH minus as a base is a strong base, negative. Now if pKb is also 15.74, K is equal to Kb is equal to 1.74 or 1.8 into 10 to the power minus 15. Minus 16, I'm sorry, I told you to check. So ultimately pK and pKb is 15.74 each. So the pK, if pKb of water is 15.74, what is pKa of its conjugate? Is equal to same 14 minus 15.74 is equal to minus 1.74. So hydronium ion is a strong acid, negative pK means strong acid, and OH minus is strong base. In fact, in BL theory, Bronsted-Lowry theory, sodium hydroxide, potassium hydroxide, calcium hydroxide, they are strong bases not due to calcium ion or sodium ion or potassium. It's due to OH minus ion. It is the real BL base. And also cyanide ion is also a BL base. It is producing some OH minus ion in excess of H plus ion, and its pOH will be definitely greater than 7. As a base, the pKb is only 4 plus 4 as we have found out. But as a base, OH minus is minus 1.74. So nearly 10 to the 5, more than 10 to the 5 times stronger is the base strength of OH minus compared to cyanide ion. So we will be discussing two aspects. In homogeneous equilibrium now, we'll be taking pH of strong acids and bases, pH of weak acids and bases, under this category, we'll be also discussing the so-called hydrolysis of salt. And pH. Then we will mix up acid with a salt, base with a salt to make a buffer solution. Now, for strong, we believe if the concentration is not very high, then H plus ion concentration is acid concentration. And H plus ion concentration is 2 times, if it is a dibasic acid, it will be believed to be all dissociated, supposing like sulfuric acid. It will be 2 times more. And there is no triprotic acid which is strong. But this is the case only in very dilute solution. Not even 0.1, because I will tell you it is a diprotic acid, but the first dissociation is 10 to the power 3. That is believed to be 100% dissociated. But what about second? The second dissociation constant HSO4 minus giving H plus and sulfate ion is 10 to the power minus 2. That is Ka2 is 0.01. So that doesn't dissociate all. So we have to find out using Ostwald dilution law how much H plus is produced. The first dissociation is complete. So that plus the second one, that is not 2 times. That is the case if you take concentration very low, less than 0.1, maybe less than 0.01, then the calculation will be futile. It will be 2 times. If it is 0.1 or in the vicinity 0.09, then the real pH won't be found by multiplying with 2, multiplying the acid concentration of sulfuric acid concentration by 2. It's not, will not help. So I'll tell you that. So obviously, supposing I will tell you, find out the pH for 10 to the power minus 5 m HCl and 10 to the minus 5 m NaOH. हाँ हेलो 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 sorry. Obviously, it's a monoprotic acid. All are dissociated. So answer will be this pH will be minus log of 10 to the minus 5. So it's 5. And for B, you have to first find out pOH is equal to 5. It is minus log of OH minus ion concentration 5. So pH I have asked. So 14 minus 5 is 9. But what about pH? Suraj Singh Om, just continue with me for another 1 hour. You will definitely find something very unique and very useful for your examination. Maybe if required, I will be arranging another class tomorrow at the same time to finish. If by any chance I cannot go to heterogeneous equilibrium, then I can arrange one more class tomorrow. But let's see, fingers crossed. But supposing I'll ask you, what is the pH of 10 to the minus 8 MSCl or 10 to the power minus 7 m NaOH? In that case, you cannot say pH is equal to 8. People will laugh at you. An acid, you are writing an acid, but you are giving the pH value more than 7, indicating that it is a basic solution. So this is a great, blunder that you are making. So in that case, normally for simple and easy calculation, we say the hydrogen ion total is equal to 10 to the minus 8. In that case, you have to add extra 10 to the minus 7 from water. Unless you add it, you can't get the correct value less than 7. So you have to add, if the H plus ion, the HCl or the acid concentration is 10 to the minus 7 or less, then you have to do this. Otherwise, you neglect 10 to the minus 7 in the face of 10 to the minus 5, 10 to the minus 6, 10 to the minus 4, 10 to the minus 3. We don't take. But only when it is 10 to the minus 7 or less, we add. So you take 10 to the minus 7 common. This is 10 to the minus 1 plus 1. So this is 1.1 into 10 to the minus 7. You will find pH will be definitely coming is about 6.9 something. I just calculated, it will be definitely less than 7. But the actual concept is not the same. This is a crude concept to get the answer quickly. But let me tell you the real concept. H2O dissociates as H plus. I sort it, make it short, condensed it to this. I'm not writing 2 water. So it's H2O, this. So but there is an additional acid, which is a strong acid. So the concentration of this is 10 to the minus 8. That is fixed. But for this dissociation, let the concentration of the uncommon ion, OH minus ion, is X. The same will be the concentration of H plus ion from water side, but from HCl side, it will be additionally 10 to the minus 8. So the total concentration of H plus is X from the water dissociation side, however small it may be, because we shall be discussing after some time, because of the common ion effect, there is a suppression of dissociation. So X value will be even less than 10 to the minus 7, but even then, we have to take it plus 10 to the minus 8 extra from the strong acid. Then Kw is always constant, which is S plus into OH minus. So this is X plus 10 to the minus 8 into X is equal to 10 to the minus 14. So you have to go for a quadratic equation. Then only you will get a value of X and then add 10 to the minus 8. Then find pH. It will be slightly different from 6 point, whatever you have got by simple addition method. But this is the real concept. Then you find X, quadratic equation, and then H plus ion concentration is equal to X plus, right? That is X plus 10 to the minus 8. Then find pH. Similarly, the second one is total OH minus ion concentration is equal to 10 to the minus 7 from the NaOH and 10 to the minus 7 from water. So it will become 2 times 10 to the minus 7. So POH will be about 7 minus 0.3. It is 6.7. So pH will be more than 7.3. But this is not the actual concept. You can't add. You have to go for the real concept is this. H2O keeps H plus and the uncommon ion is H plus supposing X. This is X plus 10 to the minus 7. So X into X to the X plus 10 to the minus 7 is 10 to the minus 14. Solve the quadratic equation. It is really time consuming. So X get how much? And then OH minus is X plus 10 to the minus 7. Find POH and then pH. So it will definitely come more than 7, but not 7.3 as you find, of course, 7 log 2. But remember, X is H plus ion concentration, but here alpha is, X by C. You have to divide by C. How many moles, which is a fraction, goes out of 1 mole? Out of 1 mole, how many moles? Moles, plural is not correct. How many mole goes? This is a fraction. So X mole goes to produce X moles of H plus per liter. Then C, out of C moles, X moles goes. Then per 1 mole, the degree of dissociation is X by C. But for you, for most of you, the Ostwald dilution law is very, very handy. Starting from 1 is very good because alpha is known. This is initial. And if alpha equilibrium, alpha is the degree of dissociation, 1 minus alpha, 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 alpha. Actually, you have not taken 1 mole. You have taken C moles per liter. So multiply C throughout. Then you do the same thing. So Ka is equal to, it will be C1C will be cancelled by 1 minus alpha. This is the original Ostwald dilution law equation. So you can neglect alpha in the denominator. But if alpha is found to be comparable with, if alpha is large, then this is rejected. Then you have to solve the quadratic equation. Supposing alpha comes 0.1, 0.2, 0.3. How can you neglect alpha? I mean 0.3, 0.1, 0.2 compared to 1? No. 0.05, 0.09, sorry, 0.01, 0.001. Yes. But if it is 0.1, 0.2, 0.3, no. This method is wrong. You have to go for the original quadratic equation to solve. And then H plus ion concentration is equal to alpha C. Simply multiply alpha, you will get. Otherwise, if you have neglected alpha, then H plus ion concentration becomes equal to Ka into C, because into C, 1C will remain in the numerator inside the square, I mean root over sign. But this is becomes wrong. And as you have to freshly find alpha by solving quadratic equation, then into C will be H plus. Same will be the case for weak base. Usually bases, like most of the bases that we study are organic bases. Ammonia is the only one which is inorganic, but all amines are NS2, secondary amine, tertiary amine, primary amine, aniline, pyridine, pyrrole. So these are nitrogen bases. They are really the bases. We borrow from the organic world to solve problems on ionic equilibrium. So they are mostly, they will accept a single proton. So unlike the case of polyprotic acids that we shall study, S2S, carbonic acid and all that, weak bases are of similar type. Supposing ammonia is a representative example. Ammonia plus water will give you ammonium ion plus OH minus ion. You know, just like we have a Hindi movie song, यही उम्र है कर ले गलती से mistake. But we have been doing गलती से mistake NH4OH. We are writing, instead of writing ammonia plus water, we blend them in the formula and write NH4OH. There is nothing called NH4OH. Yes, it is a weak base. It is very feebly dissociated and you get ammonium ion ions and OH minus ion free to a very small extent. But rest remain as ammonia, hydrated ammonia, not NH4OH. But we write. We will write. Who will do what? देखते हैं क्या होता है. We will write. So we write like this. So this is Kb. Actually, Kb expression should be ammonium ion plus into OH minus ion by ammonia. This should be. But we usually write, galti se mistake, we write ammonium hydroxide. There is nothing called ammonium hydroxide. We have been doing. Right? So, and this value is very coincidentally equal to the Ka of acetic acid. So the pKb is equal to 4.74, pKb. So same type of Ostwald dilution law will happen. So this is OH minus, this alpha is equal to Kb by C square root. If alpha is neglected in the denominator, or the original equation Kb is equal to alpha square C by 1 minus alpha. But if alpha is neglected, then alpha becomes equal to Kb by C and OH minus ion concentration is equal to Kb into 0 square root. Or else, if alpha is not small, not neglected, then you have to find alpha from the original quadratic expression, and then OH minus is equal to alpha into C, and then find POH, then pH. These are simple bases. I'm not neutral basis. I'm not taking anionic bases which will come under hydrolysis. I'm not taking cationic acids like ammonium ion and hydronium ion which will come under, hydrolysis. Or anilinium ion or pyridinium ion or pyrrolium ion, or I'm not taking any such acids. The conjugate acid of a weak base, I'm not taking that. I will be doing that under hydrolysis, but I will be telling. So, we'll talk about polyprotic acid before going to, I would think like polyprotic acid will do. Supposing we have weak, strong H2SO4 is the only case where I've told you for dilute solution, you use 2 times H2SO4 concentration. But if it is even 0.1, that will not be 100% correct. I'll tell you after we talk about the weak polyprotic acid like H2S. So such acids has 2 dissociations and 2 dissociation constants. The first dissociation is much greater than the second dissociation. This is called Ka1 10 to the minus 7, which is fortunately and coincidentally equal to the H plus and OH minus in pure water. And then the second one, HS minus, dissociates into H plus. To remove a proton from a negative ion is extremely difficult. Therefore, the Ka2 is always much less than K1. It is very fortunately and coincidentally equal to Kw. Now, the trick is find pH from Ka1 and Ka2 is equal to, since H plus is equal to HS minus, they will cancel out in the expression of Ka2. So Ka2 is nothing but sulfide ion concentration, or such, it may be sulfide, it may be carbonate, it may be sulfite, all such kind of diprotic weak acids. Now supposing I give a question, find the pH of 0.1 m H2S and Ka1, Ka2 are given, and also find S2 minus ion. Now let me find out H plus, forget about pH. pH we can find out immediately. Then HS minus, then S2 minus. Use the first dissociation constant. H2S gives you H plus HS minus. So K1 is equal to H plus, which is same as HS minus, you can make it square, and H2S. You can use the first concept, same Ostwald dilution law, but you are not using alpha concept. Straight away, if it's 0.1 and very small amount goes, so that is H plus, whatever it goes from 0.1, that is H plus, square of that, and the same as HS minus, and the equilibrium H2S is almost same as the original H2S because the extent of dissociation is so small. So we presume, and in ionic equilibrium, you have to assume many things. Otherwise, you cannot get into answer Even in 1 day, 5 days, 20 days, you will be lost in solving sometimes cubic equation, maybe higher degree equation. So of no value, absolutely no value. So this is simple. This is 10 to the power minus 7 is equal to h plus square into 10 to the into 0.1. So which implies h plus square is equal to 10 to the power minus 8. So h plus is equal to 10 to the power minus 4. So pH is equal to 4. So always find pH from the first dissociation constant, whether it is triprotic or diprotic, whatever. But I have asked Hs minus how much is same as H plus 10 to the minus 4. And if you write the expression of Ka2 is equal to H plus into Hs minus by, sorry, H plus into S2 minus, that is in the right side. So H plus and Hs minus, they are same. They are cancelled. So ultimately sulfide ion is same as the Ka2. Same thing will happen if it is S3PO4. It has got 3 Ka1, K2, K3, and they will be decreasing. Supposing this is 10 to the minus 3, this is 10 to the minus 5, this is minus 11. So the principle is find pH from the first dissociation. Then from the second dissociation, which is equal to, it will give you first H2PO4 minus, then HPO4 2 minus, then finally PO4 3 minus. So HPO4 2 minus is equal to H plus, and HPO4 2 minus is equal to Ka2, and this you have to find out using the value of Ka3 and HPO4 2 minus, which is equal to Ka2. Because in the third dissociation, HPO4 2 minus gives you H plus plus PO4 3 minus. So to find PO4 3 minus, H plus concentration you have to use. H plus is fixed from dissociation 1, we have already found H plus, PO4 3 minus is the unknown, and HPO4 2 minus is Ka2. Use Ka3, then find what is PO4 3 minus. This is all about. Now, let me tell you the fallacy, which 99.99% of the books, even for IIT, JEE and others, they don't say that. Now, H2SO4 is also a dibasic acid, diprotic acid. Its Ka is good, okay, that indicates. But K1, K2 is 10 to the minus 2. So, 10 to the minus 2 is not that very small. So, some goes, that depends on the concentration also. Now see, I'll be doing, supposing I give you 0.1 m H2SO4. So if you multiply by 2, the average books will tell you 99.99% will be H plus ion will be 2 times more, is 0.2. So pH will be equal to 2 10 to the minus 1 minus log. So it is 1 minus 0.3, approximately 0.7. 699 301. So it is 699 301 699. So you will give this answer. Actually, it is not that. Why? Because you have multiplied by 2. Second dissociation is not complete. Now, this dissociation, you say 0.1, this is also 0.1. And this is also 0.1. But that when dissociates, you have to use Ostwald dilution law concept because it is negative. You have to see how much of H plus comes. So initial is 0.100 and equilibrium is 0.1 minus x, not alpha, will not do x. So we have to find out x. So this will be x square by 0.1 minus x is equal to 10 to the minus 2. You have to find x. Then add total H plus ion concentration will be equal to 0.1 from the first dissociation and x from the second dissociation, which is not 0.1. It will be less than maybe 0.08, something like that. So then find pH. You will find it will be 0. Maybe 9 something. It's, check. It will be drastically, convincingly different from what you got. It was 0.2, so it was 0.699. Now it is 0.18, 0.17. So if that concentration of H plus ion is reduced, then pH will be increased. Now it's time for hydrolysis. Immediately we'll go for common ion effect and do solve problems. Buffer solution is a byproduct. Buy one, get one free. Once you learn the concept of common ion effect and solve problems, buffer solution is nothing but a homogeneous equilibrium with a common ion effect. That's it. So talking of hydrolysis, why I discussed hydrolysis now? Because I have already told you that anions are Bl bases. They produce OH minus in water, and many people call it hydrolysis. So salt of strong base like Na plus, K plus, these are strong for usual purpose. We don't have K plus or rubidium ion or cesium ion is not available in the market. Plus weak acid. The salt is of that type, pure salt. But that contains, weak acid other than 7 strong acids. I have listed HCl, HBr, HI, HClO4, H2SO4, HNO3 and HClO3. Other than that, all are weak. And of course, sulfonic acids, organic sulfonic acids. Other than that, all are weak. So the anion should be from the weak acid, conjugate base of the weak acid, and the cation will be either Na plus or K plus, which does not have any role to play with water. It will not be hydrolyzed because it doesn't form any covalent bond with OH minus, all ionic. So you are lucky if some ion is absolutely free of any hydrolysis, then only what water reacts is A minus, that picks up a proton, becomes HA and OH minus. Na plus is simply a spectator. So that cancels out, no role. So the basic dissociation I used to call it, now you call the hydrolysis of salt. Which type of salt? Salt of strong acid, strong base and weak acid. The cation is to be definitely Na plus, K plus, at the most calcium or strontium or barium. They are moderately strong, and then dilute concentration, we can take it as non-entities. They don't undergo any hydrolysis. They don't pick up OH minus ion. We don't take. It's not magnesium also. It's not magnesium. Calcium, barium, strontium. Okay, calcium is moderately strong. Strontium and barium, they are strong bases. Okay. So we call it KH. As I have already told you, I call it KB of A minus, HA. Same Ostwald dilution law kind of situation holds good. And if you H is the degree of hydrolysis, I call alpha. Alpha is, but since you are in a habit of saying H, degree of hydrolysis, say that. So same KH is equal to alpha square, CH square. So H is equal to KH by C square root. And here OH minus ion concentration, which is equal to C into H, is equal to KH into C square root. Similar. But here, this is the basic dissociation, which is equal to KW by Ka into 0 root. Is equal to KW by Ka into 0 root. So remember, this is alpha and this is Kb. And I have already told you K into Kb of conjugates is equal to Kw. So this is the acid. Usually in the data in the question, the Ka value of the acid is given. So that is to be used to find out KH. KH is nothing but Kw by Ka, because it is actually Kb. And into C, in numerator, it is OH minus in concentration. Denominator, it is degree of hydrolysis or degree of dissociation of the base, anionic base. Now, if you convert it to direct pH form, then the formula you have remembered is very handy, is pKw plus pKa. This Ka, which is in the right side, acid is on the right side, plus log C. So you need the concentration of the salt to find the pH of such salt, or pH of salt, such anionic basic solution, where cation is not playing any villain role to upset the pH. Na plus, K plus, they do nothing. So the other type of salt is the opposite, like weak base plus strong acid. Strong acid will have a partner Cl minus, Br minus, I minus. These are coming from strong acids, the 7 strong acids. ClO4 minus, SO4 minus, 2 minus, and one more, two more, 3 more, NO3 minus, or chlorate ion. And weak base from, or organic, accepting NH4 plus, ammonia and HCl. They have undergone perfect equivalence, giving ammonium chloride, aniline and HCl, anilinium chloride. So this is NH4 plus. We write BH plus in general. This is the non-entity. They will not form any covalent bond with H plus. They will completely dissociate. So they are very cool. They don't undergo any hydrolysis. So they are cool, but the only one which will undergo hydrolysis is BH. So supposing you take NH4 plus Cl minus, ionic compound. So nothing will happen to Cl minus, but H plus, NH4 plus will lose a proton and will become ammonia, and it will become H3O plus. Instead, we write what we write here. We write like this, NH4OH, because हम गलती से mistake करते हैं. We write like this. So instead of writing ammonia plus water, here you take out water from H3O plus, it will be NH4. Okay, we'll write that. So Cl minus will cancel out. as a spectator. So here also the same thing. Same thing here, the KH will be equal to, CH square by CH square, because H is neglected, it's very, very really small. So H is equal to same KH by 0 square root. And here KH is equal to KW by KB. Right side there is KB, which is given into C root over. And here H plus ion is equal to CH, that is equal to KH into C square root KW by KB C square root. So here you will find such a solution will be acidic because it contains free H plus ion. That such a solution, the first one is basic because it contains free OH minus ion. You will find pH greater than 7. Here the pH will be less than 7, acidic. This will be acidic, you will definitely find, and this will be basic. And if you make a handy equation for pH, here you got OH minus and you convert it to H plus and then pH. But here you get H plus ion. So pH will be very easy to get, is half is pKw minus pKb minus log C. Concentration is also, but the second and third terms are negative, first term is positive. But in the first category, all are positive. Similarly, the third one, that is the real hydrolysis. The real hydrolysis, because both cation and anion, they undergo hydrolysis. Nobody is non-entity. Nobody will be cancelled out. Supposing weak acid plus weak salt coming from weak acid plus weak base. Supposing this is ammonia. Supposing this is acetic acid. This is ammonia or pyridine or aniline. So the salt will be ammonium acetate. We write in a reverse style for ammonium acetate. So this is a hero for hydrolysis. Already you have seen in the second category. This is a hero for hydrolysis, the first category. So both of them will undergo hydrolysis. So we write like B plus A minus for general. B plus is here and A minus is here. Plus water. So B will accept OH, BOH. And A minus will accept H plus. So this will be HA. So this is also weak. This is also weak. So the net result will be either slightly acidic if Ka is greater than Kb, or slightly basic if Kb is greater than Ka. But both are weak, no free. So if you have to do 2 times, 1, 1, 0, 0. So 1 minus H, 1 minus H, H, H. C, 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 C. C terms cancel. So K, H. Here is the real hydrolysis. I can't say because both are undergoing hydrolysis. We can't say cationic hydrolysis, anionic hydrolysis, basic dissociation of acetate, acid dissociation of ammonium ion, both are occurring together. So we have to tell for this category hydrolysis of salt. I am constrained to use the term hydrolysis of salt for this time. So this will be, H by H square. Simply it is H square. So H is equal to KH square root. But if you multiply KB of this with Ka of this, the expression you find separately, and the KH, the KH, which is equal to BOH concentration into HA concentration by BA concentration, B plus concentration, which are equal. So this all will be cancelled out, it will be KW. So KH will be equal to KW by Ka into KB. So here H is equal to KW by Ka into KB square root. Now, if you use the basic acid dissociation constant HA, where you get H plus ion in the right side, you will find that H plus ion concentration, I am not doing the derivation, you will find KW into Ka by Kb square root. So there is no C term here. I'm not doing the derivation. So pH will be equal to half into pKw plus pKa minus pKb. So one is plus, one is minus. So if you pK and pKb are same, like ammonium acetate, for ammonium acetate is very interesting. So they cancel out. This is 4.74. This is also 4.74. So pH is equal to exactly 7. Exactly neutral. But actually, Ka, Kb might not be same. Supposing ammonium cyanide, ammonium, ammonia is 4.74 and HCN is 10, nearly 10. So they are different. So in that case, you have to use them and find whether it is nearly neutral. pH in the vicinity of 7, 6.6 to 7 or 6 to 8. If it is nearly acidic, nearly neutral means if it is slightly acidic, then between 6 to 7, slightly alkaline or basic, 7 to 8. Exactly 7 is a very rare type of ammonium acetate type of salt. It's very rare, but it will be either slightly greater than 7, slightly less than 7. But for the fourth type, I told you both are strong acid and strong base. The salt, like NaCl, like K2SO4. So one of the 7 negative ions from the 7 strong acids and one from the strong bases metal ions, Na plus, K plus, or Ca2 plus, or Sr2 plus, like that. Such ions will not be interested for hydrolysis. So simply they don't go hydrolysis. The only pure water equilibrium holds good. Some book write Na plus plus water, NaOH plus some they write NaOH plus H plus Cl minus plus water, HCl plus OH minus. So this is equal. So it's nothing. They don't have any tendency to undergo hydrolysis. They don't form any covalent bond. So remain as such. So simply water dissociation holds good. So it is perfectly neutral. pH, pOH is 7. So we have to wind. So we have done this. Salt hydrolysis. And now I feel like going for common ion effect. We will be winding up in another 10 minutes. And maybe if I get a request from you to go for another class where I'll be talking about buffer solution and heterogeneous equilibrium and solve at least 50 questions. In चुटकी में in IIT JEE last 10 years, NEET, you will find those questions. And that would have been the most important class had we come to that stage. But since I am revising, unless I give you the inputs, this class is not meant for those who are really thorough. This class is meant for those who have by chance neglected this topic. They became, this is class 11 topic, usually it's not a board, class 12 board examination question, it is class 11 question. Some students they neglect. So for them, even some bright students neglect, but you get many questions from this. So what is common ion effect? Rudra, what happened? You are joining?
Sir, I forgot about the class. My sister took that phone with her. She came now. So
Oh, such a kind of deviation happened for the first time, right? With you.
Yes, yes, sir.
Uh, you understood the quantum of the patience that I am mastering now to teach without you.
Yes,
You could realize it. But never mind
yes.
those who are watching directly from the YouTube. You are my inspiration. Therefore, I am progressing. Many are watching and will watch, I'm sure about it. You watch after the class, you watch with pen and paper in hand, you watch. The common ion effect is a very interesting effect. So we are now talking of homogeneous equilibrium, where say we see we have an acid, we want to introduce a common ion effect. We add in this same solution, add a soluble salt having a common ion, say sodium acetate or say HCl. So these are ionic compounds are believed to be 100% dissociated. So because of this, the LCP, I remind you from molecular equilibrium, the Lee-Chatelier's principle, holds good also here. If something will be in excess on some side, the equilibrium will be shifted. The position of equilibrium will be shifted in a manner that that concentration should be diminished, decreased to whatever best extent possible without affecting the K, Kb values, Kh values are never ever changed unless the temperature is changed. We are all talking about 25 degrees Celsius. The entire chapter, we are 25 degrees Celsius, ionic equilibrium. This is aqueous solution chapter. Now, the trick for solving problems on common ion effect is this is the common ion. So that the equilibrium of one, supposing this is the real equilibrium, this is irreversible process. This is a reversible process. The equilibrium is further shifting towards more left by adding a salt, which is a strong electrolyte having a common ion. Whether it is HCl furnishing H plus being the common ion, but here we take acetate ion, sodium acetate. So the dissociation of acetic acid is further reduced. As such, it is weak. It has become much weaker than that because of this. So the Ka expression holds good. This one by the undissociated acetic acid. So whatever acetic acid would have been there without the presence of any added salt will be further increased because of shifting equilibrium to the left. So it will remain as the original concentration. As such, we are taking acetic acid equilibrium concentration as original concentration. Now we are more confident. Now here, you have to apply the trick. Here you have to use the salt concentration. Because this is the original acid concentration. Here, you need not have to go for any Ostwald dilution law. Straight away, take the acetate ion is predominantly, almost exclusively furnished by the salt. So take the salt concentration and solve the problem and find H plus, which will be definitely less than what you would have got in the absence of the added salt or in the absence of common ion effect. So we say the dissociation is further, dissociation of a weak acid or base is further suppressed. The alpha is reduced. Ka, Kb are not reduced, alpha is reduced, so H plus ion concentration is reduced if it is a weak acid. OH minus ion concentration is reduced if it is a weak base. Now, similarly, if you have ammonia, and galti se mistake we are doing ammonium hydroxide, actually we should have written ammonia plus water gives you NH4 plus OH minus. Whether you add ammonium chloride, which is a strong electrolyte, remember, we don't write the ionic bond, but actually it is highly soluble, it is a strong electrolyte, ionic compound, and it will be irreversibly dissociating into ammonium ion and Cl minus. So the common ion here is ammonium ion. We would have also taken NaOH, which is a strong electrolyte, furnishing the common ion OH minus ion. So the same thing, Kb will be equal to ammonium ion, but which ammonium ion? You ask to this undissociated ammonium hydroxide, hey Baba, ammonium hydroxide, actually you are ammonia, गलती से हम mistake करते हैं. How much of ammonium ion you are tolerating, you are in equilibrium with? It will not see whether the ammonium ion is produced by itself. It will see around whatever ammonium ion is around the undissociated ammonia. It will say this one. I am in equilibrium with this much. Not the littlest ammonium ion produced from itself. So ammonium ion plus OH minus ion. So this equilibrium further shifts to the left because of the added salt. And here, this is the base concentration which is given to you, and this is the salt concentration. So the trick is here, salt concentration, ammonium chloride concentration. This is the original concentration of the base, and you find OH minus, which is reduced, much lesser than what was there in the absence of the ammonium chloride salt, and then POH, then pH. This is an impact buffer solution. Acidic buffer is nothing, but the only extra restriction is the salt should carry the conjugate base of the weak acid. Not in the case we are taking sodium as HCl. With acetic acid, HCl could have also produced a common ion effect, but not a buffer solution. You have to take sodium acetate. So weak acid plus salt containing the conjugate base of the weak acid, like acetic acid, acetate ion. And acetate ion is not available in the market. You have to take sodium acetate or HCN, or say in the blood you have carbonic acid, bicarbonate. Bicarbonate is not available in the market. It is sodium bicarbonate which you have to take. Or if you take acid as bicarbonate, you have to take carbonate ion. So this is a buffer, this is another buffer, and so on. Same principle will be applicable, and the Henderson and Hasselbalch, if you convert it to the log form, minus log form, the same expression. So pH will be pKa plus log salt concentration by acid concentration. That would have done without using the Hasselbalch, the Henderson-Hasselbalch equation. We could have done it from the first principle using Ka, putting salt concentration for A minus. But you can use this. And the basic buffer is, this has the special capacity because these two are remaining in very high amounts. This is almost full, almost not dissociated. This is due to the added salt. And therefore, this high concentration of both, they absorb, they neutralize the pH change effect. The change is very minimal. If you add a little bit of strong acid or strong base or dilute it with water, then pH change will be minimal, because there will be some plus here, some minus here, or some minus here, some plus here. Then you will find there will be change of pH. And a change of pH, I think tomorrow we shall be going for a problem, numerical session. Yeah. That you will be enjoying to the extent of 10 to the power infinite. But before that, those who are watching today, you must, complete, watch this video first. Then second video, first part will be heterogeneous equilibrium, and the second part will be problems. We'll be at least doing 50 problems, and we'll be ready with a calculator. We'll be doing all problems set from IIT JEE NEET. NEET questions are much simpler. All nowadays, gone are those days in 90s and the early 2000s where you were getting harder problems in the IIT advanced, right? But now they are restricting to the fundamentals, concepts. But they are making so twisted. Even if you are intelligent and very hardworking, if you are not focused in the examination, you might do some silly mistakes. They are twisting the question, conceptual, concept-based questions. That is better. Why to put very hard questions on ionic equilibrium? I was comparing what the students in 90s were getting in ionic equilibrium. Now what questions are being put? I have scanned for the last 15 years. I found these are tricky, interesting, but simple. Once you have the concept, a basic buffer is nothing but weak base, same like ammonia, pyridine, aniline, plus its salt containing the conjugate acid of the base. Ammonium ion. If it is ammonia, ammonium ion. If it is aniline, anilinium ion. But the other partner is a non-entity, will not undergo any hydrolysis or nothing. Simply ammonia, ammonium chloride, pyridine, pyridinium chloride, aniline, anilinium chloride, like that. So here the same thing. Here it will be POH will be equal to same pKb plus log salt by base. This is the Henderson equation. That is same, but the only difference is here it is H plus pH, this is POH. And once you get POH, you can get pH. Now, supposing I'll give you a question without telling you that it is a buffer solution, find the pH, then we'll be doing some mixing problems. You are always getting mixing problems. Mixture of two things, acid base, weak acid, strong base, weak acid, weak base, strong acid, making a buffer, making a completely neutralized, not neutralized, completely equivalence point, only a salt, and then you have to use salt hydrolysis equation depending on the type. Or if some weak partner is remaining in excess, then it is a buffer, use Henderson equation. So these things will be very easy for you. Find the pH by adding 100 ml of 0.1 m acetic acid and 200 ml of 0.0 0.01 m NaOH. So here you have to see that there will be chemical reaction. Which is the limiting reactant? The millimoles of acetic acid is 10. This into this. The millimoles of sodium hydroxide or OH minus is 2. So definitely acetic acid in excess. Had there been OH minus in excess, then the salt has no role to play. Take the OH minus and find pOH. Take the new concentration by adding the volume, 2 volumes, find the concentration, and then pOH, then pH. But since weak acid is remaining. So the salt formed, CH3CO minus formed, is equal to 8, sorry, 2. The limiting reactant is OH minus, is 2. 2 by 100 plus 200, 300. But in buffer solution, there is a ratio. So you need not have to divide millimole by millimole, mole by mole. You did not have to make it moles per liter. But I told you the concept is molarity, but there is no need. And the excess acid that you find after the neutralization is 8. So pH will be equal to, the pK value will be given 4.74. It will be given to you, plus log salt will be 2 by 8. So it will be 4.74 minus log 4 is equal to 4.74 minus 0.6. 2 log 2 is 4.14. Just check. I am going very fast to close today's program. I will not utter the word buffer, but it's a buffer solution. Weak acid with the salt containing, when I say salt, I mean the conjugate base of that weak acid, and the other partner, which is a defunct partner, Na plus K plus, has no role to play. The pH will remain. God. It has got two properties. It has got the second dissociation constant, its acidic property, which is characterized, which is characterized by Ka2, maybe 10 to the minus something, supposing minus 11, which is much less than Ka1, supposing, say. Then hydrolysis. All anions are Bronsted bases because of hydrolysis. This will produce S2CO3 plus OH minus. And the Kb, which is equal to Kh, is equal to Kw by Ka, which is Ka1 of carbonic acid. Here it is S2CO3. Minus 14 by, supposing this is 10 to the minus, I don't remember. So instead of giving a fictitious value, anyone who remembers? Google Baba, Jindabad. Yes, this is 10 to the minus 11, of the order of 10 to the minus 11. 5.6 in 10 to, I'm just not taking. And this is of the order of 10 to the minus 7. Yes. K1. So it will be 10 to the minus 7. See, compare between the basic dissociation constant and the acid dissociation constant, which is Ka2 of carbonic acid, and the basic dissociation constant is Kw by Ka1 of carbonic acid, because right side it is carbonic acid. So since Kb is greater than Ka, it is basic in nature. And the derivation I am not showing, for soft salts at moderate concentrations, it is independent of C. So pH will be equal to the average of pKa1 and pKa2 by 2. So it will be coming 8.3 sodium bicarbonate, irrespective of the concentration is independent. So the derivation, I am not doing it here. So there is charge balance concept and all that, and by doing that we get this average of K1 and K2. But coming to the type of salt NaH2PO4 minus and Na2HPO4 minus, there are 3 K values. For this one has the Ka1 is this one is K2. It is the Ka2 of phosphoric acid, and its dissociation, its basic dissociation, and this is Kb is equal to Kw by Ka1. You will find this Ka1, Ka2, the acid dissociation constant will be greater than Kb, so it is acidic. The pH you can find out. This is the average of pKa1 and pKa2 independent of the concentration. But if you take the hydrogen phosphate 2 minus, that has an acid dissociation Ka3, and the basic dissociation is equal to Kw by Ka2. So you will find Kb prime will be greater than Ka3. So this solution is basic. So you will find also putting the values pH is equal to half of pK2 plus pK3. It will be coming more than 7. But pK1 will be coming, pH for the dihydrogen phosphate will be coming acidic. pH of hydrogen phosphate 2 minus will be coming basic. This finishes our program. And guys who have not watched and will watch, have watched, will watch, will definitely put a hit the like button if you have liked it, the discussions, and you have not subscribed to my channel, please do so. Please do so. Bye bye. See you tomorrow. Maybe unless I sit tomorrow, it's not possible. I'm stopping to share and I'm closing now, saying you goodbye. Where is I'm not getting. Yes, live streaming. Bye. And 90 underscore bot saying that understand your English language. So I could not understand your English language. Please say in Hindi. Oh, हमें तुमसे प्यार कितना, तो ये तो हम तो तुम नहीं जानते, मगर जी नहीं सकते तुम्हारे बिना, हमें तुमसे प्यार. Sorry, I have designed this lecture in English. इसका हिंदी रूपांतर हम मे बी इस साल कर नहीं सकते, लेकिन अगला साल मैं कोशिश करूंगा ये पूरा लेक्चर हिंदी में दूं. हिंदी मेरा इतना अच्छा नहीं है, लेकिन मेरा हिंदी आप समझ पाओगे. समझ के बाहर नहीं होगा, समझ के अंदर होगा. बट हिंदी में कोशिश करूंगा मैं कमिंग ईयर. लेकिन इस साल मैंने तो इंग्लिश में कर दिया. कल तो होगा हेट्रोजेनस इक्विलिब्रियम एंड न्यूमेरिकल्स. बाय बाय. मिस्टर रुद्रानी.
Sir, yes.